An easy example of the conservation of energy that you can see at home is just a simple pendulum. It's just a mass on a string swinging back and forth. As it swings down from its highest starting point, it's losing height, so it's losing potential energy, but it's gaining speed, so it's gaining kinetic energy until it gets to the bottom and it's going its fastest. Then as it swings up, it's gaining height, so it's gaining potential energy, and losing speed as it slows to a stop and gets to its highest point. At its beginning raised position, all of the energy is gravitational potential. When it reaches the lowest point, it's all kinetic energy, and then as it swings up the other side, it goes all back to potential again. Let's take a look at a PhET simulation. Notice where the center of the blue mass is before and now that it's been raised up 10 centimeters. When we let it go, it swings back and forth under Earth's gravity. You can see it picking up and losing speed. The green arrow shows you the velocity, but it's kind of hard to keep track of that speed, so we'll slow it down a bit. Now in slow motion, you can see the velocity increasing as it gets to the bottom and then decreasing on the way up until it slowly comes to a stop. If you notice on the left-hand side, there's a bar graph showing you the potential and kinetic energy and the total energy. You can see the total stays constant as the energy washes back and forth between the blue column and the green column, showing you that it's going back and forth between potential at the top, right there, and kinetic at the bottom when the potential goes to zero, right there. Let's run through an example problem. What was the maximum speed of the blue pendulum in the video? We know that the mass was 1 kilogram, that was over on this side, and we know that it was raised up 10 centimeters, which is 0.1 meters. We also know that gravity on Earth is 9.8 meters per second squared. The conservation of energy says that the total energy is conserved, and we know that the total energy is the sum of the potential plus the kinetic. So we know the potential plus the kinetic at the top equals the potential plus the kinetic at the bottom. To find potential energy, it's mgh, and to find kinetic energy, it's 1/2 mv squared. Putting the numbers in, we have 1 kilogram times 9.8 meters per second squared times 0.1 meters plus 1/2 times 1 kilogram going 0 meters per second quantity squared equals 1 kilogram, 9.8 meters per second squared, 0 meters up plus 1/2 times 1 kilogram velocity squared. That gives us a potential energy at the top of 0.98 joules with 0 joules of kinetic energy and 0 joules of potential at the bottom with 1/2 times 1 kilogram times v squared as the kinetic energy. Solving that, you get 0.98 joules equals 0.5 kilograms times v squared. Bring the 0.5 kilograms over, you have 1.96 joules per kilogram equals velocity squared. Now we take the square root and we get the velocity is 1.4 meters per second.